Okay. Let's talk about binomial distributions today. So, just a really brief overview, let's bring up Bernoulli distributions. I think the classic example is to imagine a coin. Right, it's either heads or it's tails. Let's first consider a fair coin for now. Okay, so maybe the way we'd write Bernoulli distribution is we define some random variable. We could call it x1 for now. And we could say it follows a Bernoulli distribution with probability p. In this case, let's just set p to 0.5 because we're working with a fair coin. So x1, we're going to define it as representing the number of heads from flipping this singular coin. Alright, so notice something. We only have really two outcomes, right? We have either x1 is equal to 1 or x1 is equal to 0, right? You either get one head or you don't get any heads because we're only flipping one coin and we're flipping it once. So let's look at the probabilities, right? So the probability that we only get one head is 0.5. The probability that we get no heads is 1 minus 0.5, or just 0.5, right? Because we're working with a fair coin. We could also imagine that we're working with a biased coin, right? So let's call this y1. And let's say it's biased so that you're much less likely to get heads, right? So let's say it follows a Bernoulli distribution with probability 0.1, right? So you have two outcomes, y1 is equal to 1 or y1 is equal to 0. The probability that you get one head with this biased coin is 0.1. The probability that you get no heads is 0.9. So notice a few things, right? For Bernoulli distributions, you only have two outcomes, which are 0 or 1. And this is really handy because those are two pretty nice numbers. Yeah, I think that's basically the main thing. There are some really cool properties that arise from this. But let's consider if we took that one coin and we just maybe got a bunch of copies, right? So these are all the kind of same coin, right? Maybe same manufacturer. They all have the same probability p, right? So they'll all have identical distributions. It's a very key term. They will be identically distributed. And also ideally independent, right? Like one coin's outcome is not gonna affect the outcome of another. Or you could consider maybe having one coin, but you just flip it a bunch of times. So how do we represent this scenario, right? So maybe each flip, right, each trial that we're flipping, maybe a different coin, or just flipping a different flip. This can be represented as its own Bernoulli distribution, right? Because they're all the same, like, probability of getting heads. So we could call, like, the first coin having Bernoulli distribution with probability p. Maybe the second coin is x2, same deal, same distribution. x3 up until, let's say we have like n coins total, then we have some xn. It also follows some Bernoulli distribution with probability p. Okay, if we want to find the total number of heads amongst all the coin flips, we can just add all of these up. And hopefully that makes sense, right? And this is basically the logic that a binomial distribution is built on. So we define x as a binomial distribution with n trials and probability p, where p is just the probability of one trial equaling 1. Another way to write x is the sum of a bunch of Bernoulli distributions, right? Just like in the coin flipping example. To put this more into perspective with numbers, let's say we had x be the total number of heads you flipped, right? And let's say x follows some binomial distribution where you flipped it 10 times and each coin maybe has like a 0.4 probability of getting heads. How many heads would you expect to get total? I mean, intuition tells you 4, right? around 4, that makes sense. We can prove it more rigorously, but that's essentially what a binomial distribution is. It's just a bunch of repeated Bernoulli trials. To go more formally on what the probability of getting x, which is binomially distributed to equal some specific integer k, we can look at this, right? So think back to counting, and let's say x is still like number of heads. I think that's a very good way to think of binomial distributions. And let's say we wanted exactly k heads, right? We want to find the probability that this event occurs. Then, okay, let's look at this. So out of our n total trials, let's choose k of them to actually be heads. Right, so for each of these k trials, getting heads happens with probability p, right? So we have to multiply these together. But let's think about like the failed trials, right? But these really didn't happen with probability 1. They happened with probability 1 minus p, right? And there's n minus k like kind of failures, right? Just non-heads. So that's why we have to raise this 1 minus p to the n minus k power. We multiply all of this out, and this gives us a kind of long expression for calculating the probability of x being exactly some number. Using the example before, if we're trying to find maybe probability that x is equal to 4 using this old distribution, we'd have something like choosing 10 out of our 4 trials to actually be heads, right? We want exactly 4 heads. And then each head happens with probability 0.4. So each tail happens with probability 0.6, and there's 6 tails, 4 heads, 10 coins total. Okay, and 2 expressions you're going to see a lot is expectation and variance. So let's first look at the expectation and variance of a Bernoulli variable. So expectation of, let's call it x1 again. It's just going to be p, right? If we look at our expectation equation, this should make sense because it's equal to kind of all the possibilities that all the possible values a Bernoulli variable can take on, right? So that just includes 1 and 0. Thankfully for us, this 0 part makes this cancel out, so all we have to calculate is this part. So the expectation of a Bernoulli variable is just p, right? Because probability that x1 is equal to 1 is just p. So since binomial variables are just repeated additions of Bernoulli variables, we can use linearity of expectation and kind of rewrite it as this. Right, linearity of expectation means we can take these terms out. And we know they're all identical, so we can simplify this to something like this. Right, they all have distributions equivalent to x1, so we can simplify it to n times expectation of x1, which we know to be p. And this is why the expectation of a binomial variable will be np. Okay, let's take a look at variance very quickly. So variance of a Bernoulli variable. Let's try to calculate that. So expectation of getting x1 squared minus x1 squared. No, this took me so